briefly talk about, so there are a lot of interesting directions that I didn't get a chance to talk about. So there are applications of all of these to approximation algorithms. That's something I've worked on. So very briefly, so for symmetric TSP, we have this paper of with Mohit Singh and Amin Sabari, where we so here is what we do. We actually use linear programming to find a vector x such that it lives in it assigns a non-negative number to every edge of the graph, such that it has two properties. Summation of xe for e neighbor of v is equal to 2. So each vertex has a fractional degree 2. X is not integral, it's fractional. Each vertex has fractional degree 2, and summation of e in every cut SS complement is at least 2. So if x was an integral vector, this would characterize the Hamiltonian cycle, but it's not integral, it's fractional, so we have so-called a fractional Hamiltonian cycle, whatever. Now, here's the interesting thing. If you look at the vector x times 1 minus 1 over n is the number of vertices of the graph, this vector is in the spanning tree polytope. So what you get is that there exists this lambda such that lambda star mu has marginal equal to x. So probability of the edge e in lambda star mu is basically equal to xe times 1 minus 1 over n. So it's essentially xe. Okay. So for example, what do you get out of this? You get that if you look at the expected degree of vertex v, if I look at the expected degree of a vertex v in a random spanning tree, sampled from lambda star mu, this is equal to 2 times 1 minus 1 over n. Okay. So now you can use all these nice properties of a strong Rayleigh distributions to say that not only this vertex has expected degree 2, because the distribution is unimodal or concave and so on and so forth, with a constant probability, the degree of this vertex will be 2. So from this, you get that the probability that the degree of v is equal to 2 is at least 1 over e.
For each separate vertex, right?
For each vertex, this is true, yes.
I mean, how quantifiers go. So for every v, the probability is at least 1 over e, right?
Yes.
This way. Right?
Yes.
Not the probability that for every v.
For every v, the probability that this is equal to 2 is at least 1 over e.
Right. Okay. Yeah. So no miracles, right? So
yeah, it's no miracle, yeah. So in fact, constant fraction of vertices will have degree 2. Like 1 over e fraction of vertices in expectation will have degree 2. There are more interesting stuff we can prove. So if you use more negative correlation property, we can prove something like this, that if you have two vertices u and v, where they are not neighbors, then the probability that the degree of u is equal to 2 and degree of v is also equal to 2 is at least a constant. Okay. So this is sort of trivial, like from all I said so far. This one needs a lot of calculation, so we use a lot of other properties of a strong Rayleigh distribution that I haven't discussed, like negative association, a stochastic covering property, and so on. So you can prove this.
You can get other distributions that do that.
Satisfy the second one as well?
Okay, I think it was probably a quarter.
Oh, you can get a quarter for the second one. I see.
But not the maximum entropy distribution.
I see. They're not maximum entropy. Even if they have an edge, you can. So
no, not if they have an edge.
So
if they have an edge, maybe.
So if they have an edge, the proof goes true as long as the probability of the edge is not 1/2. It's like bounded away from 1/2. You can get that. But there are lots of things we don't know. Like what if this is instead of 2 is 3? Like can you prove something or more? Like if you have a bunch of vertices which do not have any edges with each other, can you prove that all of them will have degree 2? So with a constant probability. So the thing is, like, okay, the upshot is that you expect to have a lot of independence when you sample from these strong-Rayleigh distributions, but usually it gets hard to prove. And so I didn't say, we use these two properties to design approximation algorithms for TSP. It's imaginable if you have stronger statements, you may improve the approximation, or in fact, well, we studied a graphical version of TSP, which is sort of the unweighted version. So it's imaginable if you know these things better, you can get bounds for the weighted version of TSP. So that's like one open-ended direction to prove more properties of these distributions. So the question, prove more properties. Explicitly, like I think one explicit one is that if you have U, V, and W with no edge, prove that the probability that they all have degree 2 is a constant.
And you expect this to be true for any constant number of vertices?
I expect the constant to exponentially go down, but I expect this to be true for every constant.
And the more vertices you do, you get a better approximation ratio or something? Or?
No, that part is not. Yeah, that's like, it's a toy problem in understanding these things better. Yes?
That might be a naive question, but the fact that it's a spanning tree, I mean, it's a point in the spanning tree polytope, is just because it's convenient, or is there some, like, could you take any other polytope and do the same?
Oh, you mean, so this proof actually doesn't use the fact that this is spanning tree polytope.
Right, but I mean, the fact that you connect the LP to a point in the spanning tree is just a coincidence, or is it something you...
It is sort of a coincidence. It's because, I mean, in a sense, it's because a Hamiltonian cycle is really a spanning tree plus an edge. So when you scale it down by 1 minus 1 over n, essentially you're... Like
so for any other problem, it could be another polytope.
Yeah.
Similar argument.
Yeah. Okay. So that's one sort of line of works related to optimization. There is a different line of work related to counting. So counting. So I didn't talk about it, but there exists a Markov chain. It's a simple Markov chain. It's basically just the metropolis rule that if we have given an oracle for coefficient of each monomial, let's say coefficient of every monomial, say z to the s, we can generate S from mu, where mu is a strong Rayleigh. Okay. And the Markov chain is very simple. Basically, given S, you randomly delete an element of S and randomly add a new element. Okay, so sorry, this Markov chain is for dehomogeneous ones. Okay, so you randomly remove an element, randomly add a new element, and you take the transition with probability the ratio of the two probabilities. Okay, so it's a well-defined Markov chain. You can easily run it. And so we proved in a work with Nima and Rezai, from 16, my student. So we show that the spectral gap of this chain is at most 1 over Kn. Is at least 1 over Kn. Sorry, dn. D is the. So using this, you can generate samples from like DP, like KD, from like DDPPs. You can generate random spanning trees. Random spanning trees we already knew, but you can generate from any other strong Rayleigh distributions. In particular, you can compute. Okay, I deleted, but you can also compute G mu at any Z1 up to Zn where they are non-negative. You can also do that. Yes?
So is it like a discrete version of strong mixing for geodesic flows on hyperbolic manifolds?
I mean, so like the strong Rayleigh looks like it's a discrete version of negatively curved
It's actually possible because your chain comes from the Hessian of the polynomial.
Chain.
No, the transitional transitional probability matrix. So
It's doesn't come from it's the ratio of like S versus S minus I plus J. I don't see how you relate it to Hessian.
So maybe I'm confused because I saw some chain which was related essentially.
There is another paper for log concave distribution that's related to Hessian.
Yeah,
This is before that.
Yeah, but so that chain will also probably apply here.
Yes, it also applies. Yes.
Yeah, but that relates to the Hessian.
Yeah.
So probably it's somehow related to its Sasha said.
Yeah, it could be.
So again, if I'm not mistaken, so you start with polynomial there, which is like doubly stochastic. Derivative at 1, 1, 1 is 1.
Derivative of
Marginals in each variable is equal to each other.
it doesn't have to be.
You don't need to rescale.
No, we don't need to rescale. No. Yeah, actually, in order even to rescale, you have to be able to compute. So that's yeah, you don't need to rescale. So now what's the open problem? So this result basically says that for these DPPs we can compute. So if mu is a say k DPP, we can compute summation of let's say mu s, for example, or a marginal probability, or I mean summation of mu s where I is in s. We can compute these kind of quantities. Now there are these interesting questions of computing this for the same thing for mu to the p of s. So where p is some number different from 1. And so for machine learning application, there is an open problem. Like if you read the survey on DBPs, there is open problem for p equals 2. That's a very interesting open problem. So I should say we have a follow-up paper. We can now compute this for every strong Rayleigh distribution as long as p is less than 1 or less than or equal to 1. But for p greater than 1, we know nothing. And there's a lot of interest because like for p equals to 2, this would kind of correspond to like a second moment of your distribution. Or there's a different thing, different quantity which is also of interest, something like if you have mu and mu prime, it's a generalization of this. You want to estimate summation of mu s times mu prime of s over all sets s.
So, but that is sum of coefficients to the power 1.
This is the sum of each coefficient raised to the power p.
What happens if you take, let's say, power 2, but you multiply it by factorial of, you take the coefficient? It becomes easier or not? Because
there's no factorial here. I'm talking about the multilinear, multi-affine case. So the factorials.
You do this thing, but you multiply by, you take monomial, you multiply by factorial of the.
I'm saying you don't really need factorials here because it's multi-affine. There's no factorial.
So
the factorials come from when it's not multi-affine. Even in that case, we know nothing. So it's just a multi-affine case. There is no, yeah, we know nothing. I mean, we know. Okay, sorry, I should be careful. We know for both of these, we know a deterministic algorithm which gives e to the n approximation. That's a paper of me and Nima. But the interesting thing is to get 1 plus epsilon approximation for either of the two. I mean, this is easier, but okay, we don't know that. This is also related in one way or other to mixed characteristic polynomial. So the coefficient of the polynomial you get from Caddis and Singer are related to this object when p is equal to 2. So again, I'm not going to.
Permanent or positive semi-definite matrix is not, of course, that real stable, but it's that thing times factorials.
Yeah, but you cannot get 1 plus epsilon.
Huh?
For these things, we can get e to the n. So that's not an issue. The issue is to get 1 plus epsilon approximation. Maybe, I don't know. I can continue, but maybe if anybody has a question.
So for the B homework, inhomogeneous. So is there any counterexample like if it's not inhomogeneous, then it's hard to sample?
Oh, sorry. Yeah. So this good. So here I assume it's dehomogeneous. If it is not dehomogeneous, there is a follow-up paper by Lee, Jagielka, and Straw, who show that there is a different chain, who show that it actually mixes. The mixing time is a little bit slower, but it works. And basically, the rough idea is that you can actually homogenize. That's the thing. If the distribution is not homogeneous, you can homogenize it and then generate a sample from the homogeneous distribution. That's what they do. Yeah, so there are some other interesting questions. Okay, let me say 1 minute. So there is this question of extending strong Rayleigh distributions to like infinitely many variables or generate samples from that. So that's a very open-ended question, like what can be said or what do we know about these things. The reason it's interesting is that there are DPPs for continuous domain, and they are of interest. So I have a paper on them, but for a strong Rayleigh, we don't know much. So that's something, an open-ended question you can think about. There's also this connection to some other distributions you can get from pipette rounding or swap rounding. Don't have time to tell you about it, but you can ask me later. So there are questions of how those distributions are related to a strong Rayleigh distribution. Yes.
So this was more like multi-affine case, yes?
Yes.
I say you have this situation about generating distribution. So you have a bunch of positive symmetrical matrices.
Okay.
They're not rank 1. But let's say they add to identity.
Okay.
And you take the terminantal polynomial of that thing.
Yes.
You
want to compute mixed.
Some of coefficients will be 1.
Mm-hmm.
It will be a probabilistic distribution on let's say on the lattice.
Mm-hmm.
So if they're diagonal, it's actually easy to if those matrices are diagonal, you can generate as a sum of independent but that guy.
So you're saying, you're basically asking this determinant of summation of Zi AI, where AIs are PST.
Yes, and let's say some of them is identity.
Yeah, and you're assume summation of AI is identity.
Yeah.
Yes.
And I want to generate.
Yeah.
So the problem here is that you don't have evaluation oracle.
Yeah.
And we don't know, maybe it does exist because it's a mixed discriminant and still there is no 1 plus epsilon.
But so there's a special case of this where this is rank 2, and then it's closely related to this thing I was saying. There you have a evaluation oracle, but still we don't know how to do it.
Why? Even for rank 2 it's actually mixed discriminant, it's hard.
Yeah, I'm not saying it's easy. I'm saying I think there we have evaluation oracle.
For rank 2 there is no evaluation.
Yeah, if you tell me.
Mixed discriminant of rank 2.
Yeah, sorry, you're right. For rank 2, it's just mixed discriminant. You're right. Yeah, I agree.
Yeah. But this is actually because, for instance, the major problem in quantum linear optics is when instead of determinant you have permanent.
Yeah.
You would like to generate that thing.
Exactly. So this is the opposite question.
Yeah,
so far I was asking that you know the coefficient, you want to compute the polynomial, the generating polynomial or the generating function. Here you can compute the polynomial, you don't know the coefficient. So it's the opposite question.
And you want to generate again, because for instance, if they're diagonal, it's hard to compute coefficients, but you can generate distributions.
Yes.
Because coefficients will be permanent.
So
and
the question.
it's a sum of independent random variables.
Compute coefficient of, say, z to the s, for example.
So do you know how to sample from these when AIs are higher or rank 2?
No.
Is there any reason?
No, this is the question.
That's the question.
For rank 2, they give you, it's related to that question. It corresponds to, mixed discriminant of rank 2, which is, But for many of these things, there's a natural Markov chain, especially here, for example, for p less than or equal to 2, it seems that the natural Markov chain should mix. It's just we're lacking techniques to prove it. Okay, let me stop here. Sorry to keep you from lunch.